So I'm going to go through and explain my answers for Big Idea 1 through 3 review for the fall final exam for AP Chem. So number 1, it gives you two different reactants. You've got 3 grams of copper and 2.5 grams of nickel nitrate, and it asks how many grams of nickel will form. Well, this is going to be a limiting reactant problem because you are given two different masses of reactant. You're not sure which one limits the amount of product of nickel that you can produce. So I'm going to go from grams of copper, I'm going to get into grams of nickel using my mole to mole ratio. Same thing for taking the nickel nitrate into grams of nickel. If you notice, copper will produce 5.54 grams of nickel, while the nickel nitrate will produce 1.22 grams, which means that nickel nitrate is going to be your limiting reactant. So only 1.22 grams of nickel can be produced, because after that point, you won't have any nickel nitrate left over. So the next question asks, what mass of excess reactant is left over? Well, I know that I form 1.22 grams of nickel. And so the question is, how many grams of copper, your excess reactant, how many grams of copper are required to make the 1.22 grams of nickel? So I'm going to take grams of nickel that were actually produced, the 1.22, and I'm going to convert back into grams of copper. And so what I found was that 0.66 grams of copper are actually going to be used in the experiment in order to produce my product, which means since I started with 3 grams of copper and 0.66 were used, 2.34 grams are left over. And for this final problem, I accidentally messed up. This tells you, it's asking for percent yield. Remember, percent yield is what actually should be produced versus, theoretically should be produced versus what is actually produced. So theoretically, 1.22 grams of nickel should have been produced. So that actually should go on bottom because that's theoretical. What was actually produced was 4.00 grams, what they actually got in the lab. So I would take 4.0 grams, the actual amount of nickel that was produced, divided by the theoretical, how many grams should have been produced, 1.22, and you get 328%. A lot of people freaked out about this answer, but it actually tells you that you had some sort of contaminant in it if you get a percent yield that's greater than 100%. So you did something wrong. Doesn't mean that the answer is wrong. It just means that in the lab something happened. Normally your percent yield is less than 100%. All right, for the next problem, it's wanting you to write the empirical and the molecular formula. It gives you the mass of carbon dioxide, of water, and of nitrogen. And so from that information, from grams of carbon dioxide, I can figure out the mass of carbon that's involved in my compound, so 0.36 grams. From water, I can figure out the grams of hydrogen that are in my compound. Remember, it's a 2-to-1 ratio for hydrogen for moles of water. I know the mass of nitrogen that's given to me, and so from that, if I add the mass of carbon, mass of hydrogen, and mass of nitrogen, if I take those and subtract that from the total mass, which is 0.487 grams, I can figure out the mass of oxygen. Don't try and get the mass of oxygen from carbon dioxide and water. You'll end up getting the wrong answer, so don't do that. So now I have grams of all my different elements. I converted that into moles. Then remember, you divide by your smallest number of moles, and which in this case is 0.003, and then you get the empirical formula, which is C10H12NO. From that, I can determine the molar mass of this compound, which was, I believe, 163 grams per mole. I'm going to take the mass of the molar mass of the compound, 324, divided by the 163, which is the molar mass of the empirical formula, and that'll give me a whole number multiplier, which in this case is 2. So then, because my whole number multiplier is 2, I'm going to take my empirical formula and multiply all of the subscripts by 2. So C20H24N2O2. If the whole number multiplier were 1, then my empirical and my molecular formulas would be the same. All right, make sure that you read all of this. This should be very helpful, but I'm going to just go straight to the problems. Okay, here it asks you to write the electron configuration for copper ions. Do be careful because for copper it's 4s2 3d9, but remember you remove electrons from the highest energy level first, so 4s is higher in energy than 3d. So that's why I removed the 4s versus removing any electrons from d. It is paramagnetic because it has one unpaired electron. Remember, an element that is paramagnetic will be attracted to any sort of magnetic fields. S2 minus, since you add 2 electrons, all of the electrons are paired up, so it's going to be diamagnetic. Okay? Here it says, how are the photoelectron spectra of Ca2+ and Ar different? So remember, the only thing that affects your PES is the number of electrons and the number of protons. Now notice Ca2+ and Ar, they have the same number of electrons because calcium now has the electron configuration of argon once it loses 2 electrons. So the only difference between calcium ions and argon atoms is that calcium actually is going to have more more protons. And so as a result, remember your PES, if I show you this, and I cut it off a little bit, but here, remember, since it goes 1s, 2s, 2, these are higher and these require the most amount of energy to remove. So since calcium has more protons than argon, all of its peaks are going to be to the left of those of argon. Now, since they have the same number of electrons, the height of their peaks and the number of peaks are all going to be the same. It's just that since calcium has 2 more protons, its peaks are going to be to the left because it requires more energy to remove them. Okay, so I'm going to scroll down. Periodic trend. So please listen to my explanations as I go through these, because some of you guys have failed to include all the information that's required, so you wouldn't get credit on a final exam or on the AP itself. So for 3A, it says potassium has a lower first ionization energy than lithium. Well, potassium has a lower first ionization energy because it is larger. Therefore, its electrons are going to be farther from the nucleus, so it's easier to remove them. The ionic radius of N3- is larger than that of O2-. Well, since N3-, the nitride ion and oxide ion, have the same number of electrons, the only thing that's different is their number of protons. So nitrogen actually has fewer protons, 1 fewer proton, than oxygen does, and therefore the electrons are going to be less attracted to it, and therefore the ionic radius is going to be larger since the electrons are not as attracted to it since it has fewer protons. Calcium is larger than zinc. Well, zinc has more protons, so its electrons are going to be pulled more towards the nucleus, which means it is going to be smaller. Okay? D and E are where you guys kind of skipped over. If you checked your work, you need to make sure that you really understand this. So boron versus beryllium. If you look at the first ionization energy, meaning the energy needed to remove that first electron, the electrons for boron are being removed from the 2p sublevel, while for beryllium, they're being removed from the 2s sublevel. So if you compare P and S sublevels, the 2s sublevel is going to be closer to the nucleus than the 2p, and therefore, even though it goes against the trend that we would expect, since ionization energy normally increases as you move across the periodic table, since you have electrons farther away from the nucleus in 2p, they're going to require less energy to remove. So that's why boron has a lower first ionization energy than beryllium. For oxygen versus nitrogen, again, this breaks the rule, and so we need to explain why. Well, the electrons are all in the 2p sublevel, so that's not an explanation. But if you notice, if you draw the orbital diagram for oxygen versus nitrogen, the electron for oxygen that's being removed, that fourth electron in the 2p sublevel, it's actually paired up with another electron because remember, there are only 3 orbitals in p. So as a result, since that electron is paired with another electron with opposite spin, since electrons repel each other, that electron is easier to remove than the electron that is being removed in nitrogen, since nitrogen's electron is not paired. So that's why these two break the exception. And they don't expect you to memorize that exception, but if they do say, hey, by the way, boron has a lower first ionization energy than beryllium, explain why, they expect you to be able to explain that exception. All right, for isotopes, remember this is a weighted average. Okay, so you take the mass number that's given to you, multiply by its percent abundance. Remember to move the decimal place over 2 places. So this becomes 0.04, this becomes 0.03, so just be careful there. For these problems, I give you the mass number. I say, hey, what's the percent abundance? So remember, if one of them is X, because you make the 100% you make the percentage into a decimal, then the other one's going to be 1 minus X. Okay? If, for example, I told you, hey, I have a third isotope and its percent abundance is 30%, for example, then one of them would be X, the other would be 0.3, because I told you its percent abundance, and then the other one, instead of 1 minus X, since I already have 0.3 accounted for, this would become 0.7 minus X, since I want the percent abundance of these two to equal 70% because the other one is 30. So it would be 0.7 minus x. But in this case, since I only have 2 isotopes, this is the work you do. Okay? Make sure that you solve for the correct isotope. I think actually I plugged something in wonky here. I think a lot of you guys got closer to 51%, which is perfectly fine. Okay, but I'm mostly concerned about this setup. I'm sorry if my answer's a tiny bit off. All right, so for this problem, it tells me that ozone absorbs a frequency of this, and it asks for the energy in joules. And so I'm going to use E equals Planck's constant times my mu times my frequency, and I solve for this, and I get my energy. Now remember, this is joules for every photon, so per photon. So whenever you're using this formula here, you are in joules per photon. So here, it then for II, it tells me, hey, it requires 387 kilojoules per mole in order to break this bond. Are you going to be able, is this energy enough to break that bond? Well, so basically comparing this energy with this energy. Well, I've got to get this into joules per photon in order to compare them. So I'm in kilojoules per mole, I get into joules, then I get into joules per photon by dividing by Avogadro's number. You could have, of course, taken this and put that into kilojoules per mole. That would have been fine too. But when I compare these numbers, this is the energy that is required to break a bond. This is the energy that I have. So yes, I'm able to break that bond. Here for the particle diagrams, be careful because it wants you to show the correct size of the ions and the correct orientation. So if I'm comparing sodium ions, Na plus with O2 minus, the sodium ions are going to be smaller, so the circle I create is going to be smaller than that for O2 minus. So make sure that you don't miss points because you don't show something that's obvious to you, which is that sodium ions are smaller. Then, since sodium is positively charged, oxygen is going to be, the oxygen in water is going to be facing it, while here, the hydrogen is going to be facing it. Okay, I'm on to big idea 2. Here it tells me I have 2 grams of a gas, tells me my temperature, my pressure, and my volume. It says, what is the molar mass? Well, I'm going to first determine, I'm going to ignore the 2 grams, I'm going to first determine how many moles I have by using Pivner. So I solve for moles, then remember, molar mass is simply grams divided by moles. Well, I know how many grams I have, 2.0. I calculated how many moles, so therefore I can find my molar mass. For 2, it tells me my density is 1.88 grams per liter. So don't let this fact freak you out. If you're given this, or if you're given molarity, keep in mind that that represents the number of grams for every 1 liter. And so I actually know my volume. I can use a volume of 1 liter since it's 1.88 grams equals 1 liter, or that many grams per 1 liter. So I'm going to, again, solve for my number of moles. I have my volume of 1 liter here. And then I'm going to take the mass that was given to me, 1.88, divide by my number of moles that I solved for, and I got my molar mass. All right, for 3A, I'm collecting a gas over water. So remember, my total pressure is going to be my pressure of my gas plus the pressure of the water vapor. And so I subtracted, I got 744 millimeters of mercury. It then asks for how many moles of H2 I have. Well, I have my pressure, but I need to convert that into atmospheres. Or if you want to use your R for millimeters of mercury, I believe that's given to you on your cheat sheet, but I just always like to use the 0.0821. So I converted this into atmospheres. I've got my volume, I've got my R, and I've got my temperature in Kelvin. I solved and I got my number of moles. All right, so this, remember, is your Maxwell-Boltzmann graph. There are 2 different ways of showing this graph. Notice your x-axis is your velocity. So as you increase temperature, your velocity is going to increase, and so does your average kinetic energy. Remember, I treat this like a string where I pull it, so as you increase temperature, the average increases, but the width also increases, and the peak decreases. So imagine it's a string. If I did the same thing, but instead I was doing a different sized particles, remember that while your kinetic energy is only affected by temperature, the smaller your particle is, the faster its velocity is going to be, because 1/2, your kinetic energy is 1/2 mv squared. I showed that right up there. Okay, so helium is going to be, on average, the fastest, simply because it has the smallest mass. Okay, so here I give you 3 different gases. It says compare the kinetic energy. Well, since they're all at the same temperature, they're all going to have the same kinetic energy. Then it says compare the average velocity. Well, since CO has the smallest mass compared to the rest of them, it is going to have the highest velocity. I asked you to create a Maxwell-Boltzmann diagram here. Keep in mind, since Krypton has the highest mass. It's going to have the slowest, it's going to have the slowest average velocity, while oxygen is going to be the next, followed by carbon monoxide. So just make sure the peaks are getting shorter, wider, and then the average is increasing as you get a smaller particle. For D, which gas will deviate the most from ideal gas behavior? Remember, when we're talking about a gas, we are assuming that there is no attraction. So for an ideal gas, we're assuming that they're not attracted to each other. And so since carbon monoxide has dipole-dipole forces, since it is polar, while oxygen and krypton have London dispersion forces, it's going to deviate the most. Keep in mind, if I compared oxygen versus krypton, krypton would be the next one that deviates the most, because remember, when you're comparing the strength of London dispersion forces, it's whichever one is more polarizable, meaning whichever one has more electrons. Okay, again, what conditions are most likely to deviate from ideal behavior? Well, we don't want gas molecules to attract one another. And so the way that they would attract one another is if you had a high pressure and if they were moving very slowly because they had a low temperature. Okay, for 1A, it has you drawing your structures. Okay, so for carbonate, you got these. Again, you can put brackets with a 2- charge. I would have done that if I were more complete. Okay, this is carbon dioxide and carbon monoxide. So I'm assuming you guys are comfortable drawing your Lewis structures, so make sure you are. Which has the shortest bond length? Okay, well, carbon monoxide would, because it has a triple bond. Here, this is a double bond. And this, where I'm about to talk about bond order in a second for that guy. Shapes, this is trigonal planar, so go back and review your shapes. Those two are going to be linear. Remember, for pi bonds versus sigma, if you have a double bond, so like here I've got one double bond, that's going to be one pi bond, and the rest are going to be sigma bonds. Here, you'll always have one sigma bonds, so I got 2 sigma bonds total, and then the rest of any additional bonds will be pi bonds. So 2 pi bonds, 2 sigma. Here, again, just 1 sigma always, and then the rest will be pi, so 2 pi. Okay. Bond order, remember, it's the total number of bonds divided by the number of places where you can have bonds. So for example, here I've got 3 bonds divided by how many spaces? Well, I can only have 1 space to have it, so it's a triple bond. Here I've got 1, 2, 3, 4 bonds in 2 spaces, therefore it's going to be a double bond for bond order. Bond order is 2. Here I've got 1, 2, 3, 4 bonds in 1, 2, 3 spaces, therefore 4 divided by 3 is 1.33 for the bond order. Okay, and then for bond angle, since this is planar, trigonal planar, it's going to be 120 because it's 360 divided by 3. Here, 360 divided by 2 would give me 180. All right, so it says carbon dioxide can either have 2 double bonds or triple bonds and a single bond. Which one is going to be dominant? Remember, the structure that has the formal charge closest to 0 is going to be the one that is dominant. So if you calculate the formal charges, this is 0, 0, 0. Keep in mind when you're doing formal charge, it's the number of valence electrons minus the number of assigned electrons. So for example, here I've got 2, 4, 6, and then a bond counts as 1. So 7 assigned. So 6 valence electrons for oxygen minus 7 assigned gives me -1. So this is not going to be a dominant structure because its formal charges are not closest to 0, which it is for the 2 double bonds. Okay. All right, so here's where we get into the nitty-gritty from the beginning of the year where you guys need to be careful. Okay, so explain why solid potassium conducts electricity, but potassium nitrate does not. Make sure whenever you are explaining differences, as soon as it brings up intermolecular forces, you need to make sure you explain what type of intermolecular force each compound or element has. So potassium has metallic bonding, and potassium nitrate has ionic bonding. So since the electrons are free in metallic bonding, they will conduct electricity. I added the fact that when ions are free in an ionic bond, when they're dissolved, then it will conduct electricity. Okay, so I added that wasn't necessary. Here, make sure if you're explaining dipole moments, don't just say polar or nonpolar. Make sure to say, well, this is nonpolar because its dipoles cancel, or this is polar because the dipoles don't cancel. So nonpolar dipoles cancel, polar dipoles do not cancel. All right, if I'm comparing CCl4 and CBr4, the first thing that you need to do is identify what type of intermolecular force you have. And so since these are both nonpolar, I'm going to have London dispersion forces. If I'm comparing two London dispersion forces, we need to figure out which one is more polarizable, meaning which one has more total number of electrons, not valence electrons, total number of electrons. So since CBr4 has more electrons, it's going to be more polarizable. Make sure to be using those terms. Therefore, its intermolecular attraction is going to be stronger. Its LDF is going to be stronger. Iodine versus bromine. Okay, bromine has more electrons than iodine. Iodine has more electrons than bromine does, and therefore it's going to have a greater boiling point because remember, in order to boil, you just have to break the London dispersion forces. And so since iodine's London dispersion forces are stronger because it's more polarizable, it's going to require a higher boiling point. NAF versus CSCl. First task, what type of bonding do you have? Well, NAF and CSCl, cesium chloride, those are ionic bonds. And so remember, for ionic bonding, there are two factors that affect the boiling or the melting point. The first and the most important is the charge. So the greater the charge of the ions, the higher the melting or boiling point is going to be. If they have the same charge, then it's whichever compound has smaller ions. So since sodium is smaller than cesium and fluoride is smaller than chloride, then I know that sodium fluoride is going to have a higher melting point than cesium chloride does. Okay. All right, for big idea 3, it wants you to write a balanced spontaneous cell reaction. Well, since aluminum has a cell potential, this is reduction, remember, of negative 1.66, while tin has a negative 0.14, that tells me that this is going to be oxidized, so I'm going to want to flip it. So if I write the overall reaction, aluminum's being oxidized, so its Al produces Al3 plus 3 electrons. Tin is being reduced, so it's going to gain 2 electrons. Remember, you've got to multiply this top one by 2, this bottom one by 3 in order to balance it, so I get my reaction here. Since I flipped this reaction, I'm going to make the negative 1.66 positive. Well, I'm going to make the tin's going to stay negative. Keep in mind that unlike your equilibrium constants, where whenever I multiply an entire reaction by a number, I have to raise the equilibrium constant by that value. Like if I multiply by 3, I would have to triple it. Here, remember, the only thing that affects your cell potentials is flipping, not by multiplying at all. So just be careful. So the cell potential is 1.52. I know that it's spontaneous, or that, as we like to say, it is thermodynamically favorable because its cell potential is positive. Alrighty, so for here, it gives me the reaction, so that tells me that silver is going to be reduced while iron is going to be oxidized. Okay, which electrode is the anode and which is the cathode? I already wrote that there, okay, because remember, oxidation happens at the anode, reduction happens at the cathode. Therefore, since iron is losing its electrons, the electrons are going to go from iron into silver. And so if I draw my voltaic cell here, I like to show, and I love it when you guys do this, I love to show that iron becomes Fe2+ just to keep things straight, while silver ions are going to become solid silver, which means that I'm gaining positive charge in the solution here while I'm losing positive charge here, which is why nitrate needs to go into this solution and sodium ions need to go into this solution. So remember, iron is being oxidized, and so that's an oxidation. The anions go into the oxidation, or the anions go into the anode, which helps, while the cathode, the cations go into the cathode. So that can help you to be able to double check yourself. All right, if the concentration of Ag is increased, what happens to the cell potential? So if you look at your reaction, Ag plus is a reactant. So based on what we've learned so far with Le Chatelier's principle, if I increase the concentration of my reactant, I'm going to force it to the right, and therefore my cell potential is going to increase because I'm forming more. I'm going to form more product. So the reaction is going to be pushed to the right, which means that my cell potential would increase. If I double the concentration of silver, how will that affect the time? Remember, just because my reaction is being forced to the right, that does not mean my reaction is occurring faster. It just means that I'm going to end up forming more of this. So if I include more silver, not only will it force it to produce more of this, but it's going to take more time to do that. So it's going to actually double the amount of time that my cell potential will run. All right, electrolytic cells. So remember that amps are coulombs per second. So I give you 300 seconds because I gave you 5 minutes, and I said how many grams of magnesium would form. Well, since I have my ampage here, I can get into coulombs. Then I can use Faraday's constant to get into moles of electrons. Remember, I lose 2 moles of electrons, or actually in this case, I gain 2 moles of electrons for every 1 mole of magnesium. Then I can get into grams of magnesium. Here I'm given grams per hour, and I want to find the current. Remember, current is coulombs per second. So I need to convert grams into coulombs, hours into seconds. So I do get into seconds pretty quickly. Now I need to get grams into moles of chlorine, of Cl. And then from moles of chlorine, I'm going to get into moles of electrons and then into coulombs. Keep in mind, it's talking about chloride ions. I start with chloride ions, and then I'm going to produce... So hold on one sec. Calculate the current that would produce chlorine gas from that at a rate of... So actually, I did this wrong. I used just 1 mole of chloride, right? 35.45. But since I'm producing chlorine gas, and that's the number of grams that I'm producing, this shouldn't be 35. It should be 35 times 2. So this would be 1.14 or 135 amps. So I messed up there. So if you'll correct that, that should not be 35. That should be 35.45 times 2. All right. Keep in mind, these questions, these are the ones that you guys miss the most often. And so you just need to practice them because there's no excuse for getting these wrong at this point. Remember, if I take an ionic compound and I add it to water and it's an electrolysis reaction, meaning I provide energy for that reaction to occur, I have 3 possible reactants in Ki. I've got K+, I-, and water. So notice for the oxidation, these reactions were actually given to me in reverse. However, since I have I- as a reactant, not I2, I had to flip it. Same thing with water. Water is not a product. I don't start off with these guys, so I've got to flip the reaction. So that's why these guys are my oxidation. Well, these guys are my reduction reactions. And so I just compare them. I figure out which one is less negative. So in this case, the iodide is, and in this case, the water is. Then I add the 2 reactions together, and therefore I add my cell potentials together, and I get negative 1.363. Even though it's negative, I still want the number that's going to be the least negative. For copper iodide, super similar, except here I've got copper ions, iodide ions, and water again as my possible reactants. So these guys got flipped from where they were originally in this table. I find whichever one's the least negative, I add them together, and I get, so because copper in this case, the reduction is positive, I ended up just getting negative 0.198 volts. All right, for this guy, it wanted me to draw a potential energy curve. Again, remember that this is the energy of my reactants, this is the energy of my products, this is exothermic because the energy of my products is lower than the energy of my reactants. So just take a look at that. Remember, your activation energy is lowered if you add a catalyst. And that's pretty much it. Remember, the only other thing from Big Idea 4 for you to know, the higher your peak, the higher your activation energy, the slower your reaction is. All right, last problem. Oxidation numbers, please look over these rules and make sure you're comfortable with them. So copper here has an oxidation number of 0 because it's by itself. Then I go here, I look at HNO3. Oxygen is -2. There are 3 of them though, so that'll be a total of -6. But remember, the oxidation number is -2. I have 1 hydrogen, which is +1, which means in order for this entire compound to have no overall charge, nitrogen must have an oxidation number of +5. Here, -2. I like to look at nitrate, and I know that nitrate has a -1 charge. So if this is -2 times 3, that's -6. So nitrogen must be +5 in order for the overall charge of nitrate to be -1. There are 2 nitrates, which means copper. This is actually incorrect, by the way. Copper should be +2, not +1. Okay. Here, nitrogen, NO2, oxygen's -2, nitrogen must be +4, -2 +1. So the only time oxygen will ever be -1 is when it's H2O2, in which case oxygen would be -1 and hydrogen would be +1. So make sure that you get the correct answers in here.